Okay, I hope that this is working. The last take, oh, I should start my timer, went a little too long and had some kinks. So let's get going. We're going to be talking about Egyptian fractions today, which I think are quite fascinating and quite usable. So I will describe them. There's three key things we have to think of. They are a sum of distinct unit fractions. What does all that mean? Well, a sum is an addition problem, 1 plus 2, right? Distinct means that we can't repeat anything. So no 1 plus 1 plus 2, right? We need distinct numbers in each variable. And finally, unit fractions. Those are the fractions that only have 1 in the denominator, or in numerator, my apologies. So no 2 over 5, that is not a unit fraction. So to get an Egyptian fraction, we need all three of these things combined, which means it's going to be a sum of no repeating unit fractions like this one. Okay? Um, Egyptian fractions equal our fractions, right? This sum sums up to some fraction that we can write with non-numerators that aren't 1. And for example, down here, 3/4 we can rewrite as 1/2 plus 1/4. And 5/16 similarly, we can write as 1/4 plus 1/16. Notice here that, of course, 1/2 is 2/4 and 1/4 is 1/4, and that's how we can get 3/4. The history of Egyptian fractions is quite interesting. In ancient Egypt, they were used, and most notably in the Rhind Papyrus, which is a very amazing and detailed scroll. Ames, the author or scribe of the papyrus, who not necessarily did the mathematics but is translating it and writing it down, he notes that he is writing stuff from data from centuries before him, which means we can easily think of the Egyptian fractions notation as being 4,000 years prior to us, which is crazy. I'm going to show you a little bit of the notation that they did use back in the day. We have up here, notice this eye-like hieroglyph. This is the reciprocal, or we can think of it as the line in our fractions, right? This is what denoted the number 3 here, the number 3 here as being 1 over 3, not just 3. And then we can think over here, we have a special symbol for 1 over 10. It's this guy here. We don't want to write 10 dashes. And then to write 1/5, we can think of as taking our little eye hieroglyph looking thingy, and then we're going to have 5 dashes, my apologies. So if we wanted to write an equation, we could write something like this. We could take the little eye thingy. I can't draw that very well. Wow, I'm just going to copy it blatantly. Let's say 1/10 and 1/5. We're going to add those together. I'm just going to use our addition sign, and that's going to end up equaling. Normally, they would just write this. We can think of this as 3/10, right? Because 20%, 2/10, and 1/10 is 3/10. And that is like a way that they would denote 3 out of 10 things. Another like practical application is imagine that we have 5 circles. In this instance, the 5 circles are going to be cakes, and we're going to divide them amongst 6 people. Normally, we would cut each of these cakes into like 6 equal pieces, right? But that takes a lot of cutting, and especially if there's 5 or even more cakes. So instead, what Egyptians would do, and what we can do, is rewrite 5/6 as 1/2, which is 3/3, plus 1/3, or which is 3/6, plus 1/3, which is 2/6. And with that, we can just make 6 halves and 6/3. Notice here, right? There's 1, 2, 3, 4, 5, 6. So there's 6 halves of birthday cake for each people, or 1/2 of birthday cake for each 6th person. And 1, 2, 3, 4, 5, 6. And so everyone gets 1/2, 1/3, and that's much more practical. Down here, I have loaves of bread because obviously they didn't have cakes, but they did in the Rhind papyrus describe loaves of bread, which were often quite brittle and like chalky, and so dividing a loaf of bread into 6 pieces was kind of unreasonable. Plus, they had a like lack of numerals, so it was really nice to be able to keep 1 as the numerator, or as the I guess they didn't have the terms of numerators back then. But if we think of, I'm actually, do I want to keep this? It's down here. I'm just going to read this bottom part. I won't do an example since time is critical. But if we think of why we would want to demonstrate these in teaching for students nowadays, think of solving 5/18. I'll do this quick, right? If we think of what half or a third is for 18ths, we're going to see 6/18 and 9/18. Obviously, it's going to best be for us to look at the third, but we're already comparing values in a different denominator than our simplified denominator. And this is really helpful for students to kind of start thinking of common denominators, how we can add and subtract. Obviously, these are sums, right? So we get things like this is, I believe this is 4/18, which is 1 is 4/18 plus 1/18, which we can think of. I'm not going to bother trying to solve that for now. Instead, I think if I swipe over here, we're going to go to the real fun stuff, which is patterns in number theory. There's modern number theory as well as some quite old data. But in the Rhind Papyrus, Ames has a whole chart of 2 over n, a pattern of 2 over n for the odd n. I should specify this is for the odd. And down below, I will note when 2 over n is even. But for odd, if we look at 2/3, we have 1/2 plus 1/6. And 2/5, we have 1/3 plus 1/15. And let's try and analyze what kind of pattern might be going on here. Well, if let's see, 1/2 times the 3 here, we get 1/6. And we notice a similar thing here, right? 1/3 times that 5, we get 1/15. And if we look at how we're getting 1/2 and 1/3, if we add 1 to this 3, we get 4, and we take half of it, we get the 2. Similar thing, if we add 1 to this 5, we get 6, take half of it, you get the 3. So I think we can, if I delete this, we can think of this, and this notation here may look scary, but I'm going to explain it's really not, and it's helpful for later on in the bigger number theory chunk. 2 over n is going to equal 1. This is called the ceiling of n over 2. And what this means is if we divide n over 2 over here, if we divide 5 by 2, we get 2.5, right? And we're just going to go up to the next whole number. We're going to round up to 3. So that's why we get 3 for this. And then the final thing is taking n times that ceiling, which happens to be 3. So that's how we get 1/3 plus 1 over 3 times 5. And there you go. This is the pattern. It's a constant. What's cool and what's interesting is in the Rhind Papyrus, Ames doesn't always use this pattern. Sometimes there are values, I think 1 over 61 is one of them, that he does something different. And there are mathematicians and historians who analyze that and try and figure out why was the pattern, because they clearly were aware of the pattern. Also note, the reason that we use the odd ends is because 2 for an even number is just going to simplify into a unit fraction. 2 over 16 is just 1 over 8. And that's not as impressive as something like up here, right? Okay. We're now going to go into the greedy algorithm and Fibonacci. First of all, who is Fibonacci? Fibonacci is an Italian mathematician from around the 1200s. His name was like Leonardo, I believe. And he's regarded, if not as Fibonacci, his nickname as Leonardo of Pisa. And he wrote the Liberace, which is a very interesting, I think there's two C's, I want to say. I think I'm misspelling that. But the Liberace, which is most notably a text where he introduces the numbers that I am writing here, right? Previously, those weren't used. These are Arabic Hindu numerals, and he introduced them to Europe. But he also spoke on Egyptian fractions and even wrote what is called the greedy algorithm. And this can be used to generate an Egyptian fraction for any fraction. I note that I'm saying an Egyptian fraction. Oh, wow. Because there are technically an infinite many Egyptian fractions for any given fraction. I wanted to show that on the last slide with the 5/18. There's two different plausible ways to write that using just basic arithmetic, but there is technically an infinite. And the greedy algorithm, which I have written right down here, is going to generate the biggest, the largest, and the most concise with the least number of terms. But if I delete this here, we're going to solve 3/29 using this greedy algorithm as our last step of the presentation. Note here, of course, the a ceiling notation shows up again. That's why I had it in the presentation a little earlier. So let's begin. You may not know what I should write, this is iterating. What modular arithmetic is, this mod x, but I will describe it and you don't need to know too much about it. It's just a fancy way of thinking congruence. A big thing that I do want to point out is you can't cancel this negative y and y because of how modular arithmetic works, but that's all. I'll go into it. So let's start. We're going to have 1 over the ceiling of 29 over x, which is 3. And if we do 29 divided by 3, we're going to get like 9 point something, which means the ceiling is 10. Plus negative 29 mod 3. Mod 3, you can think of modulo, which is the word that mod is representing, as measuring. And then y, which is 29 again, times that 10. I'm just going to write 10 because we already determined that this equals 10. So if we do this, what modular arithmetic means and what the negative in this instance means is if we add 3 to 29 up until we get something that is between 1 and 3, or 0 and, 1 and 3, we're going to stop when that happens. So if I add a bunch of 3s, I'll get negative 26. And if I keep going, eventually if I add 30 or 10 3s, I'll get 1, which is really handy because what I want is 1 as my numerator for a unit fraction, right? So 1 over 290. And that means we can rewrite 3/29. And thanks to the greedy algorithm, we know that equals 1/10 plus 1 over 290. Thank you very much for watching and listening to this presentation. I hope that this all worked out. I'm sorry if I went a little long. I wish I could have gone through more. This is honestly one of my favorite topics to talk about and research, so thank you.